because this is a composite function, f of 2x, what I can do is I can make the substitution here, and I can say let w be equal to 2x. So then when I go to take that derivative, I get dw dx is equal to 2, dw is equal to 2 dx. And I like to go ahead and solve it all the way out. So 1/2 dw is equal to dx. You see where I got those two things from? So then what we're going to do, though, is when we make this w is equal to 2x, I want to go back and look at these bounds of integration and express them in terms of w. Because when we change from x to w, we're going to change the bounds of integration as well. So I'm saying when one of my bounds of integration is x equals 0. When x is equal to 0, w is equal to 2 times 0, because w is 2 times x. So that means that w is equal to 0. And when x is equal to 2, that means w is equal to 2 times 2. So w is equal to 4. Because there's secretly, like, you could write x equals 0 to x equals 2 here, but nobody does because it's so much work. But when we change from dx to dw, we can change these bounds as well. Does that make sense? So now we're going to change this. We're going to have from 0 to 4, because now we're doing things in terms of w. F of w times 1/2 dw, which then I can pull this 1/2 in front because it's a constant. And then I have the 1/2 times the integral from 0 to 4, f of w dw. One of the things is it doesn't really matter what the variable is. So even though this was integral from 0 to 4 f of x dx, and this is integral from 0 to 4 f of w dw, that's the same thing. Like, you could call it f of z, f of whatever, as long as it's f of w dw or f of z dz. 1/2 times 2, which would turn out to be 1. So the big insight there is I can replace that integral with 2. I already know what it is from given information.